Hello and welcome to the Meren video presentation for our final project of a lab in data science. I'm Louis Bossetto and our two other members are Frank Schmutz and Carl Gerard. In this project, we built a robust journey planner. So it's a journey planner where the user can specify a minimum probability of success and our planner is guaranteed to satisfy those constraints. In this video, we'll see how we did this, the assumptions we made, we'll go over the beautiful visualization we've built for it, and then I'll explain how we evaluated our approach. This was all done using Swiss public transport data from 2017 to 2019 in the Zurich area. So from this data, we first built a graph where each edge is a trip from a public transport line. We were very careful to compute two important values, which are the expected arrival delay and the standard deviation of delay for each trip. We add walking edges to this graph because we want to be able to walk for some part of the journey. On this graph, we'll run two algorithms. First, a Dijkstra's shortest path algorithm, which doesn't assume any delay and allows us to compute the shortest path from the destination station to every other station in the Zurich area. Now that we have this information, we use DFS to explore multiple routes and avoid exploring routes that will never make sense thanks to the information of Dijkstra. And as we explore routes in the DFS, we make sure that they satisfy the constraints specified by the user. Our assumptions for this project are first that we don't care about contingency plans. Second, walk distances are computed as the crow flies. And the third big assumption is that we notice modes of transport, such as bus, have no actual departure or arrival specified, so we always consider them to be successful. And here is now the visualization I was talking about. We'll run first a simple query going from this station to this station. We want to specify the departure time, which is going to be 13th September 2017 at, say, 12:20. So you have to specify the minimum probability of success, here 0.95, and we added a neat little feature where you can show a heat map of how far you'll be able to go in an amount of time that you specify in minutes. So let's see how far we can go in 30 minutes. And here's the result. Everything in green is what we can reach in 30 minutes from the heat map we specified. Here's a summary of our trip, and then you can click on each node to see exactly what you have to do. And now let's see how we validated our approach. So actually the way we did this is we didn't use any of the data from 2017 to compute average delay or such values. We used them to check that our model would make sense. So we run random queries and then see what happens. I won't go over every single graph here because they're all in the report and we don't have enough time. But here we can see something interesting. So this is the fraction of successful trips depending on the required probability of success. Except here we only consider some random queries where the fastest route has a probability of success lower than 80%. So kind of risky routes. And here we see that when we have a probability of success of 0%, this is basically the SBB website as it currently exists. We only have 75% of successful trips, so not very satisfying. Also interesting to see is the average departure time lost or arrival time lost compared to the fastest routes. So when we just consider 500 random queries, these values are quite low, so 1 minute here and 3 minutes here. But again, when we consider the risky routes I was talking about earlier, these values are much higher. Lastly, it's interesting to see how our algorithm fares in terms of performance. So here we have the computation time in seconds depending on the trip duration. And we see that, of course, it increases with a peak at 80 seconds. Here you go. That was our presentation for the project. I hope you enjoyed it, and thank you for your attention.